Alrighty, in this video we're going to be talking about 1.1, real numbers. In this, basically you just need to know what real numbers are. So we'll just call this all real numbers. We'll start off with natural numbers, which is abbreviated as an N. And they are what we call our counting numbers. So 1, 2, 3, and so on and so on. In the math world, if you ever see those three dots, this means that the pattern is going to continue. After natural numbers, we have what we call whole numbers. And it includes all the natural numbers plus the zero. So if you think of it like this, here is your natural numbers box. Your whole numbers would be part of the natural numbers plus the zero. Then you would have what we call integers, which include all of the negative numbers on the non-decimal version. So that would be ... -3, -2, -1, 0, 1, 2, 3. So therefore you can see that the integers have the negatives, but it still has the 0 for the wholes and the counting from the natural. So in this sense, if a number falls in the natural, it's also considered a whole and an integer. But notice if it's an integer, meaning let's say it's -3, does not necessarily mean it will be a whole or a natural. -3 is not a whole or a natural. Then we have what we call rational numbers. Rational numbers are numbers that can be written as a fraction. So you have like 0.3 repeating can be written as 1/3. You have 0.5, which can be written as 1/2, and then any other type of numbers of those. So all of the natural whole integers can technically be written as fractions because they get like 2. 2 can be written as 4/2. Then you have what we call irrational. These are your numbers that the decimal does not repeat, and then just and doesn't end. So it just keeps on going. So, like for instance, another example of rational will be 0.5625. It ends, so therefore this can be written as a fraction because we can simply go to the place value. So this would be the tenths, hundredths, thousands, 10,000. So this would be 5,625 over 10,000, and now we have a fraction. Irrationals cannot do that. Examples of those would be like pi, e, um, let's see, square roots of 2, square roots of 3, any square root that can't be simplified. Cannot think of any others. But basically, anything that you cannot write as a fraction will be irrational. But irrational numbers are still real. So notice if it's rational, it's got if it's a natural, it's also considered to be a whole, integer, and rational. But if it's irrational, it's only irrational. And then all of the rational and irrational are considered to be real numbers. Imaginary numbers do exist, and that's a discussion for a different day. In this lecture video, we're going to be talking about a lot of just simplistic things that you might already know or things you're learning for the first time. But I got to make sure you understand our terminology and our symbols before really showing you the fun stuff. So the next thing we need to talk about is inequality symbols. So we have what we call the less than sign. So if A is less than B, this would read as A is less than B. I know you can't physically see me, but if you would just raise your left hand and make an L, that also indicates your less than symbol. And if you can remember one, then the other one by default must be what we call the greater than symbol. So if we have something that's written like this is considered as A is greater than B. So I don't need y'all to see it as Pac-Man eats the bigger number. I need you to actually be able to read these symbols. Then we can throw in things like A less than or equal to B. So again, this would be A is less than or equal to. That's big. So for instance, I can say 2 is less than or equal to 2. That's a true statement because 2 is equal to 2. And I can also say 2 is less than or equal to 3. Also true because 2 is less than 3. So it just has to be true for one of these statements. Either A is less than or A is equal to. And we have the other direction as well, as A is greater than or equal to B, and written as A is greater than or equal to B. There you go, right there. So those are the symbols there. We also have what we call set builder notation. This is all in your book. I'm just trying to highlight the important stuff so you're not stuck having to read a textbook. So set builder notation is written like this. So it looks something like this. An actual example could be like x is a set of all real numbers such that, this little bar right here means such that. So x is all real numbers such that x is less than 3, right? That would be what property P means. So x has some property and it's a real number, right? So again, x would be all real numbers such that x is less than 3. So that'd be every number that's less than 3. All right, so that's kind of how you read it. And you can write it out like this as well when we're talking about like domain and range when we get to that point. All right, so while we're talking about set builder notation, there is a thing that looks like this. Now, as you can see, I'm not the best artist, but these are called cursive brackets. Do your best. I do not count off because you cannot do it perfectly. I think if I slow down, I think this is what it's supposed to look like, but I don't have that kind of patience. So if you see something like this and there's nothing inside these brackets, this is actually called an empty set. That means whatever you were looking for, there is nothing in it. And it could be simply you have a bag full of marbles and you want to know how many red ones there are, and there could be 0 red ones, so it would have an empty set in it, right? That's all that represents. So different type of notations that you could see is we have what we call interval notation, which you're probably more familiar with. Notation. And then again, we have this set builder notation. So I'm going to do an example of each. So if I have an interval notation of parentheses, A, comma, B, parentheses, what this basically means, it's every single numbers in this set that's between A and B, but not including A and B. So if I wanted to write this out in set builder notation, I would say X is all real numbers such that A is less than X, which is less than B, stating that X is between all as the number that's between A and B, but not including A and B. So X has to be greater than A and it has to be less than B, but it cannot be equal to. When we change these parentheses to what we call brackets, these brackets actually mean that they are included in the set. So now when I write this out as set builder notation, I can say A is less than or equal to X and less than or equal to B, indicating that now X is all real numbers such that X is everything between A and B, including A and B. And you can have a mixture of these, so we can say parentheses A comma B bracket, and that would basically just be X such that A is less than X, which is less than or equal to B. So another way to say this is if it has a parentheses, there will be no line underneath the inequality, and if it has a bracket, there will be a line underneath the inequality. And I can go the other direction with this as well. I can say bracket A be parentheses, and now I have something like this, which now I'm stating it's all the stuff between A and B, but now A is also part of the set, but not B. Other notations you might see as well is something that looks like negative infinity to B. And you can use a parentheses or a bracket here, but this will just basically state that X is less than B. All right. So every number that's less than B, that would be what that represents. You could also see something like this, and I'll kind of change it up a little bit, but let's say bracket A, comma, infinity, parentheses. This is now stating that X is our real number such that X is greater than or equal to A. And that's another way to say it. A couple of things to also note here. Infinity signs always get parentheses because infinity is not a number. It is a direction on the number line. So when you're ever dealing with infinities and you're confused on if they're part of the set or not, they always get parentheses. This tells us a direction. All right, the next thing is absolute values. The book shows it to you as this. So these little bars that look like the such that bars, if you have it on both sides of it, is now called the absolute values. And it's one of the very first piecewise functions that we typically deal with. And it basically just states if the absolute value is a positive number, it will stay positive. Nothing will change to it. But if A is less than 0, it will be the negative version of that. So basically, if I plug in the absolute value of -5, the result will come back out as 5. The way I like to teach it is how the next box is and looking at a number line. So what this basically means, absolute values are the distance from 0. And anytime you ever measure anything, we don't go, well, that's about -6 feet, because that's not something we do. We still say 6 feet, just might be below ground level, right? So absolute values, distance from 0 is always going to be a positive result. So again, an example, if you have the absolute value of -5, the answer is going to be 5. If you have the absolute value of 4, the answer is still 4. The answer always has to be greater than or equal to 0, because I can take the absolute value of 0 and still get 0 out of it. A couple of properties to kind of look at in this sense is the absolute value of A has to be greater than or equal to 0. So these are some properties. The absolute value of -A will equal the absolute value of A. So again, note if I plug in this, absolute value of -5 was 5, and absolute value of 5 is also 5. Because again, if you think about it as the distance from 0, -5 is still 5 numbers from 0, and +5 is still 5 numbers from 0. A itself can technically be less than the absolute value of A, or it can be equal to. So if this is a 5, the absolute value of 5 is 5, so they will be equal. But if this is -5, this is going to be less than the absolute value of -5, which will become 5. If you take the absolute value of A times B with inside it, this is actually going to equal the same thing as the absolute value of A times the absolute value of B. So you can do it together, or you can do them at separate moments. Same concept here. The absolute value of A divided by B is the same thing as the absolute value of A over the absolute value of B, pending that B doesn't equal 0, because that's not a real number. But that's true for division as well. Now, a triangle inequality, something that we'll talk about, we may or may not talk about, but definitely on the advanced side, is if I have the absolute value of A plus B, this has to be less than or equal to the absolute value of A plus the absolute value of B. And if you put it in an example here, let's take, let's take, let's say A is -5, and let's say B is 3. So that would mean the absolute value of -5 plus 3. You can think of any numbers you want, but -5 plus 3 is -2. And then the absolute value of negative 2 is 2. If I look on this side, absolute value of negative 5 is 5. Absolute value of 3 is 3. So 5 plus 3 gives you 8. So 2 has to be less than or equal to 8. This right here, again, is called a triangle inequality. And basically what this right here represents is the hypotenuse of a triangle. And these two represent legs. So if I add the two legs up, it has to either be equal to my hypotenuse, which would basically make a straight line of 180 degrees, or most of the time is these two legs have to be bigger than the hypotenuse for it to actually form a triangle. And that's something that you might have learned in geometry, but not something that we're going to super dig into, just an interesting topic if you want to get further into it. Now, being that this is our first lecture together, the way I design things is I like to review everything that's kind of in that section, just in case you don't read the book yourself. The good stuff comes up. The rest of the book does have great examples you can go back to. The Hawks Learning has great examples to work through with an AI helper as well. But what I also like to do in the rest of this video is I like to also kind of go over some questions you'll see on the homework. So that you have that as a guide as well. So what we're going to do is I will be working on on exercise 1 on page 12 in your book. And I'm just going to do a few. I'm not going to do all of them. But on number 1, it basically says which element of the following sets are either natural, whole, integer, rational, irrational, real, or undefined. And then on your homework, it's just going to give you a single number and ask you to check all the boxes that it belongs to. So for example, let's look at 15 over 0. Can the denominator be 0? If you think about it for a little bit, hopefully you understand that this is not true. So we call this undefined. But if you think of it like this, if you have 15 cookies and no friends get any cookies because you don't have any. Versus if you have no cookies and 15 friends, so let's say on this one here, 0 over 15, then that means that each friend of yours will get 0 cookies because you don't have any cookies. So when you have 0 on the bottom, you cannot divide 0 into a number, but you can divide a number into 0 and it always comes out as 0. So moral of the story, if 0 is the denominator, the answer is always undefined. And if 0 is the numerator, the answer is always 0. I got something that usually hangs up in my room, and I have something like this where 0 is on the bottom. That's a no, that can't happen. And if I have 0 over k, that's okay because that will equal 0. Little funny thing, if you like it or not, you can utilize it. All right, so that's the first two. So 15 over 0 would technically be undefined. That's what it'd be considered. And this one being 0, this would actually be considered a whole number. But if it's a whole number, that means it's also an integer. And if it's an integer, that means it's also a rational. And then I don't know if real is an option. I don't remember. But all these numbers would technically be considered real as well. I guess a couple of things. So whole is written with a W. I guess I shouldn't use I for integers. I is actually written as Z, and then rational numbers are actually written as Q, and real is technically written with an R. So I'll abbreviate this for you. So W is your whole, Z is your integers, Q is your rationals. I, by the way, would be your irrational. And then this would be your real. So again, I want you to notice if we go back a couple of slides, I got the result of 0 as my answer. So it fell in the whole. And if it's in the whole, that means it's part of the integer and the rational and the real. So you would check all of those boxes, not just whole. All right, let's look at a couple more. Let's look at the number negative 33. Being that it's a negative whole number, you can say that this is a integer. And if it's an integer, it'll also be rational. And if it's rational, it'll also be real. All right. If we look at example 2, we'll just kind of keep this train going. If we look at 5 square roots of 7, if the square root cannot be simplified to a nice number that can be written as a fraction, this is where we'll call it irrational. So an I would represent irrational. Alrighty, and then let's look at -1. Again, that's a negative whole number, so that would be considered an integer, which would then be considered a rational, which is considered real. Notice irrational also is a real number. Let's do one more, the 22 over 7. Notice 7 does not go into 22 evenly. You can technically write this more or less as 3 and 1/7. So it's not a perfect number, so it's not going to be a counting number, which is natural, whole, or an integer. But it is something that can be written as a fraction. If it could be written as a fraction, we would call this a rational number, which is also real. All right, so hopefully that's a good amount of examples for you. But as I go through examples, if you still need help, feel free to email me and I can do more examples as well with you. All right, let's look at example 10. In this set, it says select all the symbols from this inequality set that can be placed in the blank to make each statement true. So we're looking at -3.4 blank -3.5. All right, so one of the biggest mistakes that students make dealing with negatives is they assume a bigger negative means it's a bigger number. But I need you to think as negatives as debt. Do you want to owe someone $3.40 or do you want to owe someone $3.50? And if there's a better situation, then that number would be your greater sign or your greater number. So in this case, -3.4 is a better deal than -$3.50. So therefore, -3.4 is greater than -3.5. Also, on a number line, if this is -4, this would be -3, and then 0 would be here. -3.4 is further up on the number line, so therefore -3.4 would be bigger than 3.5. All right, let's look at another one. Number 14. You have -1/4 and -1/3. Again, dealing with fractions. If you like to, you are allowed a TI-inspired calculator, TI-84, Desmos, for function calculus, scientific calculus. You are allowed a calculator in this class. So turn them into decimals. -1/4 is the same thing as -0.25. -1/3 in your calculator will come out as -0.3 repeating. And then just ask yourself, which one's a better deal? Would I rather owe 25 cents or would I rather owe 33 cents? So hopefully you're saying, well, 25 cents is a better deal. So therefore, -1/4 must be greater than -1/3. And again, it's further up on the number line as well. Alrighty, let's look at number 27 then. On this set here, it says describe each of the following sets using set builder notation. And it says there may be more than one correct way to do this. So we are given a set as -6, -3, 0, 3, 6, 9. Okay. Best way to work these type of problems out is identify a pattern. So hopefully you're going, well, to go from -6 to -3, I must add 3. To go from -3 to 0, I must be adding 3, and then so on and so on and so on. So I must be adding 3 to my number. So when we look at this, we need to realize, all right, so if I want to write this out in a linear form, this +3 you're looking at is like your slope intercept. So if or you're not your slope, your slope in itself. So that would be the number that you would multiply to X or something like that. So the way we would want to write this, and when you have something in the situation, you start off your curly brackets right there. Whatever the difference is, will go there, and then the letter of your choice, I'm going to use X, and that's your first set. Now you just got to say, all right, this works out anytime X is between what numbers? Well, now we just got to look at it. 3 times what will give us -6? Hopefully you're saying -2. And then you go 3 times what will give me 9? Hopefully you're saying 3. All right, so then we got X in the middle of those, and then we would basically at this point, since these are included in the set, we'll do the less than or equal to and less than and equal to, stating that 3 times x works if x is between -2 and 3. However, if we keep it like this, it can be including all the decimals. I only have integers here. So I want to also state, basically state, we'll use a comma here. We'll state that not n, sorry, think of the number, x is a integer. So you can write it out like that. Another way to say this is you can write it out like this as well, where you can say x is in the family of, or this is also included in integers. So basically you're stating that x is between -2 and 3 as long as x is all the integers. So now we're bounded to, all right, that's -2, -1, 0, 1, 2, and 3. So this is probably the most complicated question you'll probably deal with in this section, but that's basically the breakdown of it. And it works out every time on whatever your pattern is. So if I was adding by 5, again, you would go 5x, and then you just figure out 5 times what would give me that first number, 5 times what would give me that last number, and then again, if it's listed like that, just state that it's an integer. All right. Let's look at number 36 now. And in this section, it says write each set as an interval using interval notation. All right, so we basically have a set builder here where x is all real numbers such that -3 is less than or equal to x less than 19. All right, when putting this from set builder, so this is set builder, to interval, you want to think of an interval. This is where you use the parentheses and brackets. So what I like to do is I'll start off with my numbers, so -3, comma 19, because that's what interval will look like. If it has a line underneath the inequality, that means it's less than or equal to that. So that tells me it's going to be included in the set. If it does not have a line underneath it, that means it can only be less than but not equal to, so therefore get a parentheses. This now tells the reader -3 is included, but all the way up to 19, but not including 19. And that would be it. Let's look at another one. Let's look at one like 37. So I got x such that x is less than 4. All right, so this one only has the one number. So I know in interval notation, I'll have a 4. But now I need to determine, is it going to be an infinity or a negative infinity? When you're dealing with a less than sign, that means you need to go to the left of the number line. So that would tell you negative infinity. Had that been a greater than sign, that tells you you need to go to the right side of the number line. So that would be a greater than sign. So again, infinities always get parentheses. And then your 4 here, since it's just less than and not equal to, it would also get a parentheses. So you can kind of look at it. X is less than 4. That means every number that's less than 4, but not including 4, is included. All right, let's jump to the next set. Let's look at example 48. And in this section, you're just evaluating the expressions. So you are giving negative absolute value of -11. So when dealing with what I call PEMDAS, but I guess now it's GEMDAS, with grouping, you want to deal with the grouping sets first. So deal with the things that are parentheses, brackets, absolute values, square roots, fractions, whatever they might be, deal with those first. So the absolute value of negative 11 would just be 11. So I put that now in parentheses because now I've done the work. The absolute value of negative 11 gave me just 11. Then you apply the negative and you get negative 11. So this guy right here is just 11, and then you can apply the negative to get the negative 11. Let's look at another one. Let's look at number 50. This one is negative 4 minus 9, the absolute value of it. So again, we're going to do the inside first. So 4 minus 9 gives me negative 5. Now I'm going to work out the operation of absolute value. So the absolute value of negative 5 is 5. And then I drop down the negative, and then I apply it. So therefore, my answer will be negative 5. You also might be looking at this going, do I really need to write 4 steps to do this? No, you can do some of this in your head and then get to the same answer as long as your future self knows how to do it as well. Let's look at one more in this set, and let's look at number 53. This is negative absolute value of negative 4 minus absolute value of negative 11 of the absolute value of that. So you deal with the first, let's make these absolute values a little bit bigger so we're not getting too lost. So I do the most inner grouping. So here is my first group in absolute value, and then within the absolute value, I have another absolute value. So what I do here is I'm going to say, well, the absolute value of negative 11 is 11, right? That whole thing gives a positive 11 out of it. Now I'll do inside this absolute value, so negative 4 minus 11 gives me negative 15. Now I'll work out this absolute value, so the absolute value of negative 15 is 15, and then I apply the negative at the end. All right, so again, notice I did the first inner absolute value first, then brought down everything, then I worked out everything inside that absolute value, brought everything else down, then I worked out that absolute value, and then applied that negative that just kept on writing at the very end. All right, last question. That should cover everything in this section. So let's look at example 60. It says, find the distance on the real number line between each pair of numbers given. So you're going to be given something like A equals 8 and B equals 3. It does not matter if you do A minus B or B minus A when finding distance, but the goal is that you need to take the absolute value of the result. So this would also equal this. Let's prove it. So we get 8 minus 3, and we'll do 3 minus 8. So 8 minus 3 would be 5, and then 3 minus 8, which is negative 5. So this would give me 5, and this would also give me 5. So regardless if you do A minus B or B minus A, as long as you do the absolute value of it, you get the correct answer because you're just trying to determine how many numbers are between A and B. Now you might be able to look at this and go, well, there's 5 numbers between 8 and 3, and that's your answer. That's simply all you're doing when trying to find the distance. All right, so that will conclude our first lecture on 1-1. Again, as you go through this, if you find yourself having questions, feel free to email me. We can definitely work some more out. But until the next video, bye for now.